In the 1940s, we had this theory called quantum electrodynamics, QED for short. It was supposed to explain how light and electrons interact with each other. And you know what? When we did simple calculations, the thing worked beautifully. I mean really beautifully. We could calculate things and they'd match the experiments to incredible precision. But then we tried to be a little more careful, a little more precise. We wanted to include what we call the second order effects, the small corrections, and that's when all hell broke loose. Let me explain what happened. You see, according to quantum mechanics, an electron sitting there isn't really just sitting there doing nothing. No, no, no. It's doing all kinds of crazy things. It's constantly emitting photons, little particles of light, and then reabsorbing them. Emit, absorb, all the time. These are what we call virtual photons. They exist for such a short time that you can't actually see them directly, but they're there, and they affect what the electron does. Now, here's where it gets interesting. When you try to calculate the energy of an electron, taking into account all these virtual photons, it's emitting and absorbing, you get infinity. Not just a big number, infinity. The electron should have infinite energy. And not just infinite energy, but infinite mass too. And its charge, the electric charge that we measure, that should also be infinite. Now you might say, well, that's obviously wrong. An electron doesn't have infinite mass. If it did, you couldn't move it at all. This is clearly nonsense. And you'd be right. It is nonsense. And in the 1930s, when people first got these answers, they thought, well, this theory must be wrong. We've got to throw it out and start over. But then something very curious happened. A few people, Schwinger, Tominaga, and I, we all came to the same idea, more or less independently. We found a way to get rid of the infinities. We called it renormalization. And let me tell you what this procedure is. It's the most ridiculous thing you've ever heard. Here's what we do. We say, all right, we got infinity for the mass of the electron. But look, we never actually measure the so-called bare mass of the electron, the mass it would have if it wasn't surrounded by this cloud of virtual photons. No, what we measure in the laboratory is the total mass, the dressed mass, the mass including all the effects of the virtual photons. So we play a little game. We say, let's suppose the bare mass is also infinity. But it's a special infinity, exactly the right infinity, so that when you add it to the infinity from the virtual photons, you get a finite number. And that finite number is the mass we actually measure, 0.5111 million electron volts. Now you're probably thinking, wait a minute, you can't just subtract infinity from infinity and get whatever number you want. And you'd be absolutely right. This is not sensible mathematics. Sensible mathematics is when you neglect something because it's small. You don't neglect something because it's infinitely great and you don't want it. But here's the amazing thing. When we did this, when we played this game with the mass and with the electric charge, the theory started working again. And not just working fantastically well. We could calculate the magnetic moment of the electron to 10 decimal places, and it agreed with experiment. 10 decimal places. This is the most accurate prediction in all of science. Let me show you what we're doing with a picture. Imagine I draw a Feynman diagram, those little pictures I invented to keep track of these calculations. You have an electron, and it's emitting a photon and reabsorbing it. This makes a little loop in the diagram. And when you calculate the contribution of this loop, you have to add up the contributions from photons of all possible energies, all possible momenta. Now, the photons with low energy, low momentum, those give finite contributions. No problem there. But as you go to higher and higher energies, higher and higher momenta, the contributions don't die away. They keep adding up. And when you try to integrate over all possible momenta, all the way to infinity, the integral diverges. It becomes infinite. So here's what we do. We say, all right, we'll cut off the integral at some very large momentum, call it lambda. We won't integrate all the way to infinity. We'll stop at lambda. This makes everything finite. Then we adjust the bare mass and bare charge, these quantities we can never measure, so that they cancel out the dependence on lambda. And then at the end, we let lambda go to infinity anyway. It's hocus pocus. It's a shell game. We shuffle the infinities around until they disappear into these unmeasurable quantities. I called it a Dippy process. Despite the clever name renormalization, it's what I would call not legitimate mathematics. And yet it works. That's the thing that gets you. It works so well that you can't ignore it. Now, why does this bother me? Well, several reasons. First, we haven't proved that this procedure is mathematically consistent. We can do it order by order in perturbation theory, fine, but we've never shown that the whole series makes sense. I suspect, actually, that it doesn't. I suspect that renormalization is not mathematically legitimate. Second, it suggests that our theory isn't really fundamental. If we have to cut off our integrals at some large momentum lambda, maybe that's telling us something. Maybe there's some new physics at very short distances, very high energies that we don't understand. Maybe QED is what we now call an effective theory. It works at the energies we can reach in our laboratories, but it's not the complete story. Let me give you an analogy. Suppose you're trying to understand water. You can describe it as a continuous fluid, and you can write down equations, the Navier-Stokes equations, that tell you how water flows. These equations work beautifully for understanding rivers and ocean waves and bathtubs, but they're not the whole story. If you look closely enough, you find that water is made of molecules. There's a smallest scale, the molecular scale, where the continuous description breaks down. Maybe space-time is like that too. Maybe if you could probe distances of 10 to the minus 33 centimeters or so, the Planck length, you'd find that space-time isn't smooth and continuous anymore. Maybe there's some kind of graininess, some kind of structure, and maybe that's what the cutoff lambda really represents, our ignorance about what happens at these incredibly tiny distances. There's another piece to this story that's quite beautiful, though. It's called the renormalization group. This was worked out later by people like Gell-Mann and Lowe, and especially by Kenneth Wilson, who got a Nobel Prize for it. Here's the idea. When you do these calculations, you have to make a choice about exactly how you do the renormalization. You have to pick a scale, an energy scale, or a length scale, where you define what you mean by the mass and charge of the electron. Different choices give you different values for these parameters. Now that might sound like a disaster. How can the mass of the electron depend on your choice of scale? But it turns out that this is actually a feature, not a bug. The physics doesn't depend on your choice of scale. If you change the scale, the mass and charge change in just the right way so that any actual prediction you make, anything you can measure, stays the same. And this leads to a remarkable idea. The charge of the electron, what we call the coupling constant, actually depends on the energy at which you measure it. At low energies, the charge has the value we all know, about 1 over 137 in certain units. But if you could measure it at very high energies, you'd get a different value. The charge runs with energy. Why does this happen? Well, remember those virtual electron-positron pairs I mentioned. When you have a charged particle, it's surrounded by a cloud of these virtual pairs. The virtual electrons are repelled from the real electron, and the virtual positrons are attracted to it. So the virtual positrons screen the charge. They partially hide it. Now, if you probe the electron from far away, you see the screen charge. But if you could get closer, you'd bypass some of the screening and you'd measure a larger charge. Higher energy means shorter distance. So at higher energies, you measure a larger effective charge. This is actually a very physical picture. The infinities are still there in the formalism, but now we understand them differently. They represent the contributions from all the quantum fluctuations at all scales, from the very large down to the infinitesimally small. The renormalization procedure is a way of organizing our ignorance about the shortest scales. Let me tell you something else interesting. In QED, the charge increases as you go to higher energy. But in quantum chromodynamics, QCD, the theory of the strong nuclear force, it's the opposite. The strong force charge, what we call the strong coupling constant, decreases as you go to higher energy. At very high energies, the quarks inside protons and neutrons act almost like free particles. We call this asymptotic freedom. It's one of the beautiful features of QCD. Now, where does all this leave us? Well, QED is an incredibly successful theory. As I said, it makes predictions that agree with experiment to fantastic precision. But is it a complete and consistent theory? I don't think so. I think it's what we now call an effective field theory. It's valid up to some very high energy scale. But beyond that, something else must take over. Maybe it's a unified theory that combines electromagnetism with the weak nuclear force and gravity. Maybe it's something we haven't even imagined yet. The thing that still bugs me, even after all these years, is that we're sweeping the infinities under the rug. We're not really solving the problem. We're finding a way to calculate around it. And that makes me think that we're missing something deep, something fundamental about how nature works at the smallest scales. You know, Dirac, one of the great physicists of the 20th century, he never liked renormalization. He said it was just not sensible mathematics. He thought we needed to find a completely different approach, and maybe he was right. Maybe someday someone will come along with a better theory, a theory that doesn't have these infinities in the first place. But until then, we're stuck with renormalization. It's a tool that works. It lets us make predictions. And as physicists, we can't ignore something that works just because we don't like the way it works. Nature doesn't care about our aesthetic preferences. There's a lesson here, I think, about how science progresses. We don't always move forward with beautiful, perfect theories. Sometimes we have to use tools that are a little bit suspect, a little bit hocus pocus. We do what we have to do to make progress, to calculate things, to compare with experiment. And along the way, we hope that someone will figure out what's really going on. That's what happened with renormalization. It started as a desperate trick to get rid of infinities. Now we understand it better thanks to the renormalization group and effective field theory. But I still think there's more to understand. I still think nature is trying to tell us something with these infinities. You see, the infinities appear when we assume that space-time is perfectly smooth and continuous all the way down to infinitely small distances. But maybe that's not true. Maybe space-time has some kind of structure at very small scales. Maybe there's a minimum length, a fundamental graininess. Or maybe our whole way of thinking about quantum fields is wrong at very high energies. I don't know the answer. Nobody knows the answer. That's what makes physics exciting. We have this incredibly successful theory, QED, that makes the most precise predictions in all of science. And yet it's built on a foundation that we don't fully understand. It's got these infinities lurking in the equations, and we've learned how to tame them with renormalization, but we haven't really explained them. So when people ask me about renormalization, I have to be honest. Yes, it works. Yes, it's led to tremendous success. But do I understand it? Do I think it's the final answer? No. I think it's a signpost pointing towards something deeper, something we haven't discovered yet. And you know what? That's okay. Science isn't about having all the answers. It's about asking the right questions and being honest about what we do and don't understand. Renormalization is a perfect example of that. It's a technique that works brilliantly for practical calculations, but it also reminds us that we still have fundamental questions to answer about the nature of space and time and quantum fields. That's what I wanted to tell you about infinite energy and why we had to renormalize physics. It's a strange story full of infinities and hocus pocus and tricks that somehow work. But it's also a story about the honesty of physics, about admitting when we don't fully understand something, even when we can calculate with it successfully. And maybe, just maybe, the next generation of physicists, maybe some of you, will figure out what's really going on. Maybe you'll find the theory that explains why renormalization works, or maybe you'll find a better approach that doesn't need renormalization at all. That would be something to see. Until then, we keep calculating, we keep comparing with experiment, and we keep wondering about those infinities, because that's what physicists do. We use the tools we have, even when they're a bit dippy, and we never stop asking why.